Okay, today we're going to discuss the topics in the number theory, which are the greatest common divisors, Euclidean algorithm, and fundamental theorem of arithmetic. So let's start with the greatest common divisor. So the greatest common divisor is very common to us because this is already introduced to us when you were in our bachelor's degree or even in our basic education days. So we have here that the greatest common divisor or the GCD of the two integers a and b, not both zero, is the largest positive integer that divides both a and b. That is denoted by parentheses ab. So example for that is, for example, if we are going to get the GCD of 12 and 18, answer is 6 because 6 is the greatest integer that can divide 12 and 18, which can have um, a natural number. Okay, so because the GCD of a and negative b is just the same with the GCD of negative a and b, and that's also the same with the GCD of negative a and negative b, which is also the greatest common divisor of a and b. So we confine our discussion with the GCDs to the positive integers. Okay, so here are the symbolic definition of the GCD. So a positive integer d is the GCD of two positive integers a and b if you have d divides a rather and d divides a, and if the d prime divides a and the d prime divides b, then uh, the d prime is less than or equal to d, where d prime is also a positive integer. Thus, the d is the greatest common divisor if the two conditions are satisfied. So you have there the d must be a common factor of a and b, and d must be the largest common factor of a and b. In other words, any other common factor d prime must be less than or equal to d. Okay, so the discussion, okay, in the next discussion, we hope to develop an efficient method for finding the GCD of the two positive integers. So there are positive integers whose GCD is 1. For example, you have the GCD of 6 and 35. So accordingly, we have a certain definition for that. Okay, so let's have the relatively prime integers. So two positive integers a and b are relatively prime if their GCD is 1. That is, if the GCD of a and b is equal to 1. So we have your theorem. So you have any two consecutive Fibonacci number are relatively prime, meaning that the GCD of the two Fibonacci numbers that are consecutive with each other is equal to 1. Okay. With that, we have here the lemma. Um, we have, which is also known as Duncan's identity. So we have let f sub I denote the ith Fermat number. Then you have the product of the consecutive Fermat number up to n minus 1 is equal to f sub n minus 2, where n is greater than or equal to 1. Okay, so using this result, we can um, we now show that the two distinct Fermat numbers are relatively prime with each other. Okay, so now on the second theorem, that's in Polya, 1925, let m and n be distinct non-negative integers, then the f sub n and f sub n are relatively prime. Okay, so the same we have here the theorem number 3. there is an infinitude of primes. So meaning to say that there are many primes present in our number system. Okay. So we have here another theorem. So let uh, the GCD of A and B is equal to D, then A over D, then the GCD of A over D and D over B over D is equal to 1, or they are relatively prime. And the GCD of A and A minus B is equal to D. Okay. Now let's move into the concept of the linear combination. So linear combination of the integers A and B is the sum of the multiples of A and B, that is the sum in the form of uh, alpha A plus beta B, where alpha and beta are integers. So for example, if we have uh, three, uh, 2 times 3 plus 5 times 7 is a linear combination of uh, 3 and 7. Okay, so we have a theorem, next theorem. So the GCD of the positive integers A and B is the linear combination of A and B. Okay, let's have an example. Okay, for example, express the GCD of 28 and 12 as a linear combination of 28 and 12. Okay, so first notice that for our solution, okay, for the solution, take note that the GCD of 28 and 12 is equal to 4. So we need to find integers alpha and beta, okay, such that we have um, alpha times 28 plus beta times 12 is equal to 4. So in this case, we can have the trial and error. And through trial and error, we could have alpha equals 1 and beta is equal to negative 2. In other words, for our final answer, we can express the GCD of 28 and 12 as 1 times 28 plus negative 2 times 12, which is equal to 4. Okay, that's our final answer. Now, take note that the values of alpha and beta are in the linear combination need not to be unique. So for instance, we could also say that the linear combination of the GCD of uh, 28 and 12 can be, you have negative 5 uh, times 28, okay, plus 12 times 12. So this is equal to 4. So again, when we are expressing the linear combination, okay, the alpha and beta are need not to be unique. Okay. So we have this theorem, theorem number 6. If D is the GCD of A and B, and D prime is any common divisor of A and B, then the D prime divides D. Okay, so we have here the what we call as the alternate definition of GCD. So A positive integer d is the GCD of a and b if d divides a and uh, d divides b, and if the d prime divides a and d prime divides b, then d prime divides d, where d prime is the positive integer. Okay, so with this, we could have a theorem, the seventh theorem in this presentation. So you have let a and b and c be any positive integers. Then the GCD of AC and BC is equal to C uh, times the GCD of A and B. Okay, so we have another theorem based on this alternate definition of GCD. So you have two positive integers A and B are relatively prime if and only if there are integers alpha and beta such that the linear combination of the A and B is equal to 1. Okay, so another theorem we have here. Two positive integers a and b are relatively prime if and only if there are integers alpha and beta such that the what we call this one, the linear combination of a and b is equal to 1. So with this, we could have the corollary. So if d is equal, if d is the GCD of a and b, then the GCD of uh, a over d and b over d is equal to 1. Another, we have if the GCD of a and b is equal to 1, and this also the GCD of a and c, then the GCD of a and bc is equal to 1. Another corollary, if a divides c and b divides c, and the GCD of a and b is equal to 1, then ab divides c. And another corollary, we have if a and b are relatively prime, and if a divides bc, then a divides c. Okay, so we have the GCD of n positive integers. So the definition of GCD can be extended in uh, three or more positive integers. So we have here the GCD of the n, which is greater than equal to two positive integers. So you have a sub 1 to a sub n is the largest positive integer that divides each a sub I. It is denoted by, we have this one. Okay, so let's have an example. So for example, we have here find the GCD of 12, 18, 28, 12, 36, 61, and 180, and we have 15, 28, 50. So for the first GCD, so for the first example in this presentation, so clearly that the GCD of 12, 18, and 28 is equal to 2, since only number 2 can divide the three numbers 12, 18, and 28, okay, into an integer, a positive integer. Now, for the second number, the GCD of 12, 36, 60, and 108, in this case, we have to look for a number that can divide these four numbers, okay, the largest integer that can divide these four numbers into positive integers. So the answer for this one is 12. And for letter C, so you have the GCD of 15, 28, and 50 is equal to 1. So for in this case, 15, 28, and 50 are uh, what we call this one, relatively prime with each other. Okay, so we have another theorem. Okay, so let the a sub 1 up to a sub n, okay, b n, which are greater than equal to 3, are positive integers. Then the GCD of a sub 1 up to a sub n is equal to the GCD of a sub 1 to a sub n minus 1 and a sub n. Okay. So let's have an example. Using recursion, evaluate the GCD of 18, 30, 60, 75, and 132. So for in this case, we could have, um, for the solution, so we could have the GCD of 18, 30, 60, 75, and 132. This can be expressed as the GCD of 18, 30, 60, 75, and you have 132. Okay, and then you could now have the GCD of the GCD of 18, 30, then you have 60, then you have 75, then you have 132, which can also be expressed as you could have the GCD, okay, of the GCD of the GCD of the GCD of you have uh, 18, 30 of the 60, okay, of the 75, okay, and 132. So which is actually equal to the GCD of 18 and 30 is 6. So you have the GCD of 6 and 60, then the GCD of 75, then the GCD of 132, which is equal to um, the GCD of 60 and 6 is equal to 6. So you have the GCD of 6 and, I forgot, okay, 6 and 75, then you have 132, which is equal to the GCD of 6 and um, 75 is 3. So the GCD of 3 and 132 is equal to 3. Therefore, the GCD of 18, 30, 60, 75, and 132 is 3. Okay. So we have here the corollary. Okay, this is actually taken from the previous presentation. Okay, that follows by the induction. Okay, now we have here if D is equal to the GCD of A sub 1 to A sub n, then the D divides A sub I for every integer I, where I is greater than or equal to 1 but less than or equal to n. And then we also have another corollary. Okay, if the D divides the product of A sub 1 to A sub n, and the GCD of D and A sub I is equal to 1 for I greater than equal to 1 but less than equal to n minus 1, then D divides A sub n. So um, we have this one. This is taken into consideration of the corollary. Okay, so we have the pairwise relatively prime integers. For the positive integers a sub 1 to a sub n are piecewise or pairwise relatively prime if every pair of integers are relatively prime. That is, the GCD of a sub I and a sub j is equal to 1 whenever I is not equal to j. So here we have the corollary. If the positive integers a sub 1 to a sub n are pairwise relatively prime, then the GCD of a sub 1 to a sub n is equal to 1. Okay, and then we have another corollary. So there are infinitely many primes. Okay, so for the corollary, okay, in this presentation, um, it only mean for instance, you have the GCD of 18, 15, and 49. Okay, these are pairwise relatively prime because the GCD of 8, 15, and 49 is equal to 1. Okay, now beware that the converse of this corollary is not true. Okay, that is, if the GCD of a sub 1 to a sub n is equal to 1, then the integers a sub 1, a sub 2 to a sub n need not to be pairwise relatively prime. So for example, we have 6, 15, and 49. Okay, so 6, 15, and 49 is equal to 1. However, if we are going to pair this number, the 6, 15, and 49, let's say you have 6 and 15, okay, and 49 are not relatively prime because you have 6 and 15 is not relatively prime with each other. Diba? Okay. So that's the reason. Okay. So let's have Euclidean algorithm. So um, in Euclidean algorithm, okay, so there are procedures that exist for finding the GCD of the two positive integers. One efficient algorithm is the Euclidean algorithm that is named after Euclid, okay, who included it in his book, okay, the uh, the book, The Elements. Okay, so the algorithm, however, was most likely known before him. So it is the fundamental tool in algorithmic number theory. Okay, so we have here the theory. So you have let A and B be any positive integers and R the remainder. Then A is divided by B when A divided by B, then the GCD of AB is equal to the GCD of BR. Okay. So let's have an example, which is an illustration from the previous theorem. So um, A is equal to 120 and B is equal to 12. So first, we have to determine the GCD of 120 and 28. So for our solution, the GCD of 120 and 28 is equal to 4. Now, by the division algorithm, you have 120 is equal to 4 times 28 plus 8. Okay. So by theorem, the GCD of 120 and 28 is equal to 28 and 8. Okay. As we can see, the GCD of 28 and 8 is equal to 4. Okay. Therefore, we could also, which is the same with the GCD of um, 120 and 28. So we have now illustrated the previous theorem. So by this example, using the theorem, evaluate the GCD of 2076 and 1776. Now, for our solution, for in this case, now we are going to apply the division algorithm with the 2076 since 2076 is the larger of the two numbers. And then um, as the dividend and the 1776 as the divisor. So we could have 2076 is equal to um, a division algorithm. You have 1 times 1776 plus 300. Okay. So applying the division algorithm with 1776 as the dividend and 300 as the divisor. So we could have 1776, which is equal to, you have 300 um, times 5, okay, plus 276. Okay, now the next step would be continue this procedure until a zero remainder is reached. So you have we have 276, which is equal to um, you have 11 times 24 plus 12. Okay, so and then you have uh, 12. You have 24. Okay, 24 is equal to 2 times 12. Now, by the repeated application of the theorem, we have the GCD of 2076 and 1776 is equal to the GCD of 1776 and 300, which is equal, okay, which is equal to the GCD of 300 and 276, which is equal to the uh, GCD of 276 and 24, which is also equal to the GCD of 24 and 12, which means that the GCD, okay, of 2076 and 1776 is equal to 12. So this is now the final answer. Okay, therefore, the last non-zero remainder in this procedure is the GCD. Okay. So we have another example. So apply the Euclidean algorithm to find the GCD of 4076 and 1024. So for in this case, okay, so you have 4076 76 can be expressed as you have 1024 times 3. No? So 3 times 1024 uh, plus 1004, and then you have 1024 is equal to, you have uh, 1 times 1004 plus 20, and then you have 1004 is equal to uh, 50 times 20 plus 4. And then as you can see, you have 20 is equal to 5 times 4 plus 0, of course. Therefore, the last non-zero is 4. Therefore, we can now say that the GCD of 4076 and 1024 is equal to 4. So if you can see the pattern that the algorithm for Euclid, okay, um, you have the GCD of x, y, and the divisor. So this algorithm returns the GCD of the xy in the divisor, where y is less than or equal to x, but greater than equal to greater than zero, greater than zero. So the algorithm begins when we have the dividend, which is the x, and then the divisor is y, then the remainder. Then you have the dividend, you have modulo of the divisor, okay, while the remainder is greater than to 0. So, and then repeat until such that we have a 0. So that's the end. Okay, so the non-zero, okay, the last non-zero remainder is our GCD. Okay. Okay. So we have this one. Using the Euclidean algorithm, express 4076, the GCD 4076 and 1024 as the linear combination of 4076 and 1024. So for the solution, okay, all we need to do is to use the equation in the previous example in the reverse order. Okay. Then each time substituting for the remainder from the previous equation. Okay. So in this, what we call this one, um, solution. Okay. You have the GCD of 4076 and 1024 is equal to 4. Okay, which is equal to, from the previous example. So you have 1004 minus, you have 50 times 20. And then uh, we can substitute 20 from the previous example. So you have 1004 minus 50 times, you have 1024 minus 1 times 1004. And then we can now express this one as 51 times 1004 minus 50 times 1024. In this case, we could have 51 times 4076 minus 3 times 1024 minus 50 times 1024, which is equal to 51 times 4076 plus you have negative 203 times 1024. So our alpha is 51 and our beta is negative 203. Okay. Now, we have here the lemma. Say, let alpha is equal to, you have the quantity 1 plus square root of 5 all over 2. Then, the alpha raised to n minus 2 is less than to the f sub n, which is less than to the alpha raised to n minus 1, where n is greater than or equal to 3. Okay. So we have a theorem, okay, the 12th theorem, okay, in this presentation. So the number of the divisions needed to compute the GCD of A and B by the Euclidean algorithm is no more than 5 times the number of decimal digits in B, where B is less than or equal to A but greater than or equal to 2. Okay. And then we have the fundamental theorem of arithmetic. So we have several lemmas and corollary here. Now, we um, we now continue our what we call this one discussion of the primes. We can establish what we call this one. We can establish unequivocally the assertion that prime numbers are the building blocks of all integers. In other words, integers that are greater than or equal to 2 are made up of primes. Um, that that is, every integers greater than or equal to 2 can be decomposed into primes. So this results the fundamental theorem of arithmetic, uh, which is the cornerstone of the number theory and one of its cardinal results. Okay, so it appears in this concept is actually appears in the Euclid's book, which is the Elements. So before we state it formally and of course prove, we need to lay some groundwork in form of two lemmas. So we have these two lemma in this presentation. So throughout, we have to assume all letters denoted positive integers. So if P is a prime and P divides AB, then P divides A or P divides B. Okay. Another lemma, you have let P be a prime number and P divides A, uh, P divides the product of A sub 1 to A sub n, where A sub 1 to A sub n are positive integers, then P divides A sub I for some I, where I is greater than or equal to 1 but less than or equal to n. Now take note from the first lemma, um, we can actually prove that one. Suppose, let's say, um, P does not divide A. So if P does not divide A, then P and A are relatively prime. Okay. There are integers. If P and A are relatively prime, then there are integers, let's say alpha and beta, such that we can express that as alpha times P plus beta A is equal to 1. Okay. Then, if we multiply both sides, of this equation by B, then we get alpha times P times B plus beta times A times B, which is equal to B. Then since uh, P divides P and P divides AB and P divides uh, the combination alpha times P times B plus beta AB, okay, then we could now say that P divides B. Okay. Now, we do also have the corollary. Okay. If P, Q sub 1, Q sub 2 up to Q sub n are prime such that P divides the product of Q sub 1 to Q sub n, then P is equal to Q sub I for some I where I is greater than or equal to 1 but less than or equal to n. Okay. So, same uh, procedure. We can give that proof. Okay. So, if in this case, if since P divides the product of Q sub 1 to Q sub n, okay, it means to say that P divides Q sub I for some I. But P and Q sub I are primes. So the P is equal to Q sub I. Okay. Now, by this, we can uh, state and establish the fundamental theorem of arithmetic, the most fundamental result of in number theory. Okay, so you have here the fundamental theorem of arithmetic. Every integer n greater than or equal to 2, okay, either is a prime or can be expressed as the product of primes. The factorization into primes is uniquely except for the order of the factor. Okay. Now with this, we could have the canonical decomposition. The canonical decomposition of a positive integer n is of the form of n is equal to uh, p sub 1 raised to a sub 1, p sub 2 raised to a sub 2, up to p sub k raised to a sub k, where p sub 1 to p sub k are distinct primes, with p sub 1 less than p sub 2 less than up to p sub r, and each exponent a sub I is a positive integer. Okay. So for example, find the canonical decomposition of 2520. So we begin with the smallest prime 2. Okay. So for our uh, solution, beginning with the smallest prime number 2, so you have 2 divides uh, 2520. Okay. So we could say that 2520 is equal to 2 um, times 1260. Now, 2 is the factor of 1260. So, 2000, 2520 is equal to 2 times 2 times 630. And then again, 2 divides 630. So we could now have 2 times 2 times 2 times 315. Now, as you can see, 315 is not divisible by 2, but it is divisible by 3. So in other words, we could have 2 times 2 times 2 times 3 times 105. Now, um, 3 is a factor of 105. In this case, we could have um, 2 times 2 times 2 times 3 times 3 times 35. So in other words, the canonical decomposition, okay, of this number 2220 is actually 2 raised to 3 times 3 raised to 2 times 5 times 7. So that is the canonical decomposition of 2520. Okay, so we have find the positive factors of 60. So for our solution, notice that 60 is equal to uh, 2 squared times 3 times 5. Okay, by the fundamental theorem of arithmetic, every factor of 60 is of the form of uh, 2 raised to a times 3 raised to b times 5 raised to c. Okay, where a is greater than equal to 0 but less than or equal to 2, and b is greater than or equal to 0, and then c also is um, less than or equal to 1. Okay, so by this, we can express 60, okay, as this one. You could have um, 2 raised to 0 times 3 raised to 0 times 5 raised to 0, which is equal to 1. And then you have 2 raised to 1 times 3 raised to 0 times 5 raised to 0, which is equal to 2. And then you have 2 raised to 2 times 3 raised to 0 times 5 raised to 0, which is equal to 4. Then you could have 2 raised to 0 times 3 raised to 0 times 5 raised to 1, which is equal to 5. And then you have 2 raised to 1 times 3 raised to 0 times 5 raised to 1, which is equal to 10. And then 2 raised to 2 times 3 raised to 0 times 5 raised to 1, which is equal to 20. And then you have 2 raised to 0 times 3 raised to 1 times 5 raised to 0, which is equal to 3. And then you have, what else? 2 raised to 1 times 3 raised to 1 times 5 raised to 0 is equal to 6. And then 2 raised to 2 times 3 raised to 1 times 5 raised to 0 is equal to, you have 12. Then you have uh, 2 raised to 0 times 3 raised to 1 times 5 raised to 1, which is equal to 15. And then 2 raised to 1 times 3 raised to 1 times 5 raised to 1, which is equal to 30. And then 2 squared times 3 times 5 is equal to 60. Okay. Therefore, okay, 60 has 12 factors. Okay. Now, another theorem for the canonical decomposition. Okay, so let E denote the highest power of 2 that divides n factorial, and B the number of ones in the binary representation of n. Then n is equal to E plus B. So let's have this one. Using the canonical decomposition of 168 and 180, find their GCD. So the canonical decomposition for our solution rather for our solution, the canonical decomposition of 168 is equal to you have uh, 2 cube times 3 times 7. And the canonical decomposition of 180 is uh, okay, 2 squared times 3 squared times 5. Okay, so the only common prime factors are 2 and 3. So 5 or 7 cannot appear in their GCD. Since 2 appears thrice in the canonical decomposition of 168, but only twice in the canonical decomposition of 180, um, 2 squared is the factor in the GCD. Okay. Similarly, 3 is also a common factor. So we could have the GCD of 168 and 180 is equal to uh, 2 squared times 3, which is equal to 12. Okay, so that's the concept of the canonical decomposition. Thank you very much.